Folks, welcome to Lecture 23, Future of Computing. Woo! Okay. One of the things we're going to be doing in this is talking about where computing can go, and it's really very exciting. I'll show you some videos. But technology news in the day is Intel released recently a 50-core chip, a single chip with 50 cores in it, which already is making my mind hurt in terms of how much parallelism on one chip. Imagine if you had 20 of these things and how cool that would be. You'd have 1,000 cores there. That's pretty cool. So, and that chip, by the way, by itself can do, by a single chip, one little chip this big, can do a sustained teraflop. That's incredible. Do you guys have, 1 times 10 to the 12th floating point operations a second, which is unheard of. This was like a computer the size of this room not that many years ago, and now it's on one chip. It's like the miniaturization is incredible. So that's cool stuff. You guys know that we are doing 1080p archived lectures for this, for the online community. Today's lecture, to show you that we're going to the future, you guys know what the next level above 1080p is? It's called Quad HD. It's 4 times that. It's like 2 1080p's this way and 2 1080p's this way. This lecture is going to be produced in Quad HD. So we're recording me vertically, so I'm a little taller, and I'll fit in the beautiful Quad HD video the best. So that when you have screens that are massive, we're going to be recording. So we'll see how fast we can get this up. It's going to be amazing. And YouTube actually, as of today, as of a couple of years ago, has Quad HD support. So if you had a Quad HD monitor, you could actually watch this in pixel-for-pixel accuracy. So we're excited about this. Future of computing and future of webcasting and online learning, all that stuff. All right. So today's lecture is going to be about ways to compute things that the future may hold. Different ways that we would compute things. Now, this is not looking at the future of life and technology and computers in society, which might mean cars that drive themselves, matrix-like plugging in your head to the computer, that kind of stuff. That's for the last lecture. That's like thinking about the future of applications. This is the future of how to compute something in a different way that we normally do it today. So we'll talk about quantum, DNA, computing, biological machines, and then talk about the smart grid, because you can't talk about the future without talking about energy and smart grid. So here's growth. Here's where we've moved in the last several decades of computing. We started at the kilo level, and kilo is 10 to the 3rd or 2 to the 10th. We moved to the mega level, 10 to the 6th or 2 to the 20th. And you keep going and you can see the pattern. 10 to the 9th, you keep adding 3 to the exponent of the 10 or doubling or adding 10 to the exponent of the 2. So giga is 10 to the 9th or 2 to the 30th, and you keep going. So right now, dividing a current computer into the 3 pieces of it. A processor, the brains, memory, how much storage it has, and disk, how much kind of longer-term storage it has. And there's a blurring in there because flash is kind of in the middle. Processors have doubled in speed every 2 years, which is incredible, since 1971. This is unbelievable. That's slowed now. Professor Yellick showed you the curve slowing down in terms of that speed. What they're doing is then going parallel. Okay? It's still doubling in terms of the number of transistors we squeeze in, which is Moore's law, but the actual performance has slowed down since 2005. But we're going parallel, and with parallel code, we're still doing pretty well with that. When you graduate, I predict you're going to have a 4 gigahertz machine, meaning it's not going to be much faster than it is today, but you are going to have 32 cores. I predict that. This is Dan's prediction. Who knows? I haven't done so well in the lottery, but did pretty well with this one. Memory. Again, doubling every 2 years since 96. That's more recently it's doubled that fast. I predict you're going to have 128 gig of RAM. Just to get a sense of people in the room, how many of you have at least 1 gigs of RAM? How many have at least 2? How many have at least 4? Ooh, look at this around. Wow. How many have at least 8? 1, 2, 3 in the back, 4. How many have at least 16? Only me. All right. So what we have is, and 32 and 64 are out there. You can actually buy a Mac with 64. So that's the next level, which is crazy. I predict you're going to have 128. So that's my predict. When you graduate, they'll sell computers at 128 if you're buying a high-end machine. Disk space. The capacity has doubled every year, which is, look at that, doubled every year since 97, which is, again, doing amazing numbers. I predict when you graduate, you can't really read the red on the blue, you'll have 16 terabytes. And that may be in a RAID, but I predict you'll have 16 terabytes. All right, let's do this one. How many of you have at least 1 terabyte? How many have at least 2 terabytes? Wow, okay, this is whose house to rob. How many of you have at least 4 terabytes? Okay, 4. How many at least have 8 terabytes? Only me. Okay, so what we have, I do video processing, it makes sense. Okay, so good stuff. But here's the thing. I want you to know this scale because it's real, folks. We are going from petascale supercomputing to exascale, right? The amount of data that the human race is producing is going from exa to zetascale. You need to know these numbers and know what's bigger than what, right? You can't just be mathematically enumerate. Like illiterate is about can't read. Enumerate means you have no idea whether billions is better than millions. And there are some fraction of our politicians, by the way, for whom that's true. They really are enumerate and like trillion, it's the same as millions. But no, it's a lot more than a million. So it's important that you guys know this and that they know this as well. So I challenge my former students to come up with acronyms, metaphors, to think about that. So what we did was I challenged them saying the first 2 letters, if you have the first 2 letters, you probably can remember them, kilo, mega, giga, tera, peta, exa, zeta, and yada. Okay? So let's try this. Okay? So these are what students came up with. And by the way, each one of these has the fact that the first 2 letters is the same as these words, as these SI prefixes. Okay? Kid means giant Texas people exercising Zen-like Yoda. So you see kid, right, K-I, meets M-E, right, it all works out, right? That's pretty cool. Kind men give 10% extra, zestfully, youthfully. And that's harder because the commas, you can get those confused. I want to make sure you get the order right, so that's not as good. Kissing mentors gives testy, persistent extremists zealous youthfulness. This is like a tongue twister for me here, okay? Kindness means giving, teaching, permeating excessive zeal yourself. I like that a lot. That's a great one, right? Okay? Killing messengers, don't kill the messenger, gives terrible people exactly 0, yo. And you have to kind of do a little gang sign or something like that. All right. Kindergarten means giving teachers perfect examples of zeal and youth. Like that one, right? Okay. Kissing mediocre girls or guys teaches people to expect 0 from you. So now, I don't know about that one. And also, guys will make you think it's gaga, so it really has to be, anyway, so that's the way, just do that. Kinky, okay, the next one. Kissing Mel Gibson, Teddy Pendergrass exclaimed, zesty, yo. So that was my own thing. And then combining all of them is, this is something you could say to everybody else, kissing me gives 10% extra zeal and youth. So that's not just kissing Dan, but kissing, the speaker says that, right? So everyone goes around, tell that to your friends, kissing me gives 10% extra zeal and youth. Whatever you remember, you should know this. So if I say, hey, which is bigger, zeta or yada, go back to your acronym and do that, okay? So I expect you to pick one of these or make your own up and memorize it, okay? That's important. All right. The first and most obvious place that we're going for the future is quantum computing. And you probably heard of quantum computing, but you may not have known what it is. I've tried to distill basically unfathomable web pages to fathomable 3 slides, okay? It's hard for me to get, and I have a PhD in computer science. So quantum computing is actually quite difficult to grok. Grok means understand. So it's very new. The field is very young. Normally, you guys know we have bits, 0 or 1. That's given, right? In quantum computing, they call them qubits, okay? Or quantum bits. And those are either 0, 1, and here's the part that kind of makes your head hurt, or a quantum superposition between the two. You're like, what? Okay. Here's an example. Okay. If you have 2 bits, you have 2 possible states, 0, 0, 0, 1, 1, 0, or 1, 1. Okay? Now, what if I took 2 coins, okay, and flipped them into heads or tails or 0, 1. I write 0, 1 on each coin, okay? Flip 2 coins, and I cover them both. Now, you guys realize that they really do have a value, right? I'd sneak it. See, it's really that one. That's the real answer. But as far as you're concerned, if I'm covering it, what value do they have? They really have all 4 values with 4 equal probabilities. Does that make sense? Right? They kind of really all have all 4 values at once. That's what that last statement says. That these bits really have multiple states because you don't know what they are. And the moment you ask for them, you get a value. But when they're still kind of hidden, they're in this quantum superposition, which is they have all the states at once with some probability distribution. It might be that case, they're all equally probable. But I might reveal some more information which might change the probabilities of these guys. So it's kind of like a hidden information with some probability balances of whether each bit is a 0 or 1. Okay? If you have 2 bits, the idea is it's not that they're actually in one of these. It's in the idea of quantum computing is that they actually are in all of those states at once. That's the key idea. And that's what gives you the parallelism. They're in all of those states at once. This, by the way, is called a block sphere, and that's a way to visualize what a qubit looks like. Okay? And you can read more about that. And please do consult that. I can point you to a professor here. His name is Umesh Vazirani. If you have detailed questions about this, please go to him because he's the person who's been working this for several years, and he'll give you the real answer. So here is an interesting point. Imagine you have a problem that has these 4 critical properties. Number 1, the only way to solve it is to guess answers repeatedly, meaning you can't kind of get any information from the wrong answer you just guessed. So there's kind of no information you get from a wrong answer. There are n possible answers to check. Each answer takes the same amount of time to check. And, as I said, there are no clues at all about which answer might be better or worse. It's not like I can do something like gradient descent or kind of use my nose and kind of figure out, where things are. If I'm trying to find the fastest way from here to New York, I probably should just start walking east, right? That gives me some sense of how to get there. And maybe at one point I have to do a U-turn and go west to go east, but really, for the most part, going east is the right answer, right? The 4th bullet says, no, you can have no kind of idea that one answer is any better than any other answer, okay? This is very much like, on the top right, guessing passwords, right? You're guessing passwords on a laptop you just stole, and you basically have all 4 of these things, okay? Or that your friend just stole from you. All right. So a normal computer and a normal human would take it worst case n steps, right? The worst case is you keep trying all the possible passwords of all the possible combinations of zeros and ones or letters and numbers until finally the last one you try in the space of things you could try gets it, right? It's always the worst case, the Murphy's Law thing, right? A quantum computer can solve that at worst case square root of n. You're like, so what, right? So if n's really big, so what's the big deal? Why does this matter? Really? Let's see. Let's say you have 72 bits for a password. Passwords, the alphanumeric passwords, letters and numbers, they basically become bits, right? You know that things can become bits. So passwords become bits at the lowest level in the computer. That's 2 to the 72. With 72 bits, each bit can be one of 2 possibilities. That's 2 to the 72 possible passwords. That's a really big space. In the world where 2 to the 40 is, this is where you talk, tera. 2 to the 50 is peta. 2 to the 60 is exa. Remember, you go back to the mnemonic. 2 to the 70 is, right? Zeta, right? Exactly 0 from you. E-Z-Y. Z. Zeta. 2 to the 72 is 4, because 2 to the 2 is 4. 4 zeta possibilities. That, my friend, is a massive number, okay? So let's try it. Let's actually have one machine, our Mac lab. Oh, in fact, we're going to have all of our Mac lab try it. 30 machines in the lab, 8 cores per machine, 3 gigahertz per core. We're going to say that's 3 billion checks per second per core. That gives me 720 billion checks per second per lab, or 720 gigachecks per second per lab, assuming that every single clock you're testing it valid, like no overhead, just literally as fast as you possibly could with no delays, okay? That's a lot. That's a lot of checks per lab. Now, let's divide 2 to the 72, which is the number of checks needed, by 720 gigachecks per lab, which gives me 6.6, I did the math for you, 6.6 billion seconds per lab. This is my physics thing. Check the units. It all works out, which is 208 years. So someone steals your laptop, they have to be kind of a vampire and live at 208 years to get it, right? So Okay, so you see Edward running around. Don't let him steal your laptop. Okay, so now, nobody, Twilight, okay. So what we've got here is, and Bella too now, I understand. So well, how about a quantum computing? How about oh, that was a spoiler. Uh-oh. So quantum computer, 72-bit quantum computer. Same thing, okay? Square root of 2 to the 72 is 2 to the 36. Still a big number, right? 2 to the 6 is 64. 2 to the 30 is billion. 64 billion checks. I can do 720 billion checks a second. Therefore, a tenth of a second. Do you guys appreciate how cool that is? A quantum computer is a tenth of a second versus 208 years. So only when you kind of put those numbers into like, whoa, you mean it could actually crack all of our computers, laptops? In a fraction of a second. That's pretty way out stuff, and it's really powerful. So people are really excited about the parallelism that you get from this, the idea that those bits are in kind of all the states at once. And it's only the square root of n that lets you have to go through all those states to actually figure out which one it is. Okay? Some powerful mind-stretching stuff, but exciting. And stay on, continue to read like Slashdot and Scientific American and MIT Technology Review to see what the current newest updated news and stuff is. The next one is called DNA computing. And DNA computing is the idea that you use the parallelism of biology to solve your problem. In fact, they're already doing it now. I say to myself, how much concentration of this thing is enough to kill the bacteria? So I set up a whole grid, a microarray of maybe 1,000 by 1,000, and on each of these keys, I put a different amount of concentration of my medicine. And then I watch them all grow bacteria. And the one that kills it the fastest, while not killing other cells or whatever, is that. So basically, I put all, like this one I put in 0.1, this is 0.2, 0.3. See how I put all the different variances, and I say, now grow overnight. I come back in, and immediately I get my answer. I get that idea that the biology kind of does the work for you? So that's the basic idea of using this parallel computing, is that you could actually seed this biological creature, this biological set of cells with some data, with some input data, and they've actually, there's a paper in Nature that researchers claimed that they had done this. They had built a quantum computer, and very recently, researchers proved that they've created one of the basic logical operations, a NOT gate and an AND gate. And if you have a NOT gate and an AND gate, AND is like the logical AND from BYOB. It's only true when both of the inputs are true. And a NOT gate is like the NOT from BYOB. If you put in true, it puts out false, or vice versa. They built a NOT gate and an AND gate out of biological cells. And we know as computer scientists and computer engineers, once you have a NOT gate and an AND gate, that's all you need to build any computer. That's actually really crazy. So they claim that they have that. That's pretty exciting. So read about that. DNA computing is also very hot, but also, again, 20 years down the road. The next idea, and that's really cool, is the idea of connecting the body, a body, here just an insect, with a computer. Can you do that? Can you actually get input and output from a computer to in this case, an animal? And let me show you a video of work that was done in this department by my colleague, Michel Maharbis. Okay? The idea is he implanted an insect, a winged insect with an electrode who's able to control the winged insect's flight. Check this out. Shh.
This guy is our biggest workhorse right now, so I'll show you a video because we mount right on here. We mount a small microcontroller about this size, but a larger battery, and it has an antenna. And this guy is fully wireless, transmit and receive. So the electrodes that go into the head and into the muscles and into the pronotum do similar things as what we demonstrated with the little one, but they get told what to do remotely. And so the nicest data we've gotten from these guys, we let them fly, and then the operator will tell it from a base station, turn on, turn off, turn left to right, climb, drop, and so on.
A scientist sends a wireless signal from the laptop to the Beetle to start and then stop flight. The Beetle, seen in the upper part of the frame, is tethered for practical purposes.
Try one more time. Start again. Start. Okay.
We've also demonstrated, just because we wanted to show this work across several species, and also for payload reasons, to see what we can carry with it. we've demonstrated the same techniques with a much larger. This is a Arena beetle. This much larger one is called Megasoma, and I think the average weight of these things is in the 15 gram to 20 gram range, and we've had as big as 27 gram beetles. And for all these beetles, generally the payload capacity is about 20% of body weight. So this, you can imagine this carries much more stuff. Sounds like a helicopter when it flies. It's pretty cute. This beetle we use to demonstrate, because it has such a large head region because of this horn. We use it to demonstrate our ability to implant rather large things into the segments inside the body. So we've implanted in pupil phase, while it seems pupae, we've implanted an entire microcontroller with leads that come out for the battery and the electrodes, stimulators that go to all different. When it emerges, you can't see anything because the cuticle fuses around it. So inside this is an entire TI microcontroller. We're sitting essentially in this segment.
Here, the beetle is attached to a clear plate so that its flight pattern can be better observed. An oscilloscope next to the insect shows the electrical signals as they are delivered. A short oscillating pulse triggers the animal to flap its wings, and it continues flapping until a short signal pulse tells it to stop.
You don't have to, the way the beetle's brain works, it's not sending a fly, 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 fly continuous signal. It just says start flying, and it stops, the brain stops sending the message, and it goes into fly mode. So the brain goes back to sleep, and then it says stop flying. It's kind of like a button that you have to keep hitting, stop and start. It's not not a light switch where you go start, and there's like, and then stop. It is hit a button, start, hit a button, stop. And all they did was figure out what that button was, measure it, and then simulate it themselves. And it turns out, what I've been told is that beetles love to fly. Like this is not painful for them because, this is what I'm told. Who knows about beetles' pain? But the point is, the beetles, they're not. It's just like all they do is go zip, a little burst. And it goes, oh, I'm flying. I'm happy. I'm flying. And then they go zip, stop, and that's it. And there's a little bit of extra work to get them to actually change the right and left. But they, in theory, have actually shown work that they can actually tilt up and down and then go left and right, which means you can actually fly this thing around like. In Brookstone, you can now buy beetles that are, I'm joking, but the idea is you can now control this like you could a helicopter. Pretty cool stuff. And the idea, by the way, the uses that they're thinking about for this, just to let you know, is to save lives. You can imagine a situation where, in, say, wartime, it's too dangerous, it'd be too hard or something to have a little teeny helicopter, but if you just kind of had the beetle, it looks like the beetles that live in that area, and you can kind of like have a beetle look over an area and say, are the bad guys there, and do some stuff. Yes, question?
So this wouldn't be going on with larger animals? It would just
That's, from what I've seen, it was no try to control large animals. It's just about beetles for for security reasons. Maybe you can send a beetle, because by the way, one of the things that'd be cool is if you could tell, like, imagine trying to find earthquake survivors, right? And maybe a robot can't get into that space with all the things that might get stuck, but an animal, a beetle, if you actually could just keep crawling toward the person, right? You train a beetle like that a person always has food, so it gets near the person, then you lose contact, it'll just keep hunting toward the person to find the food because they think a person has food and they'll come feed me or something, right? So you can imagine training. I don't know if you can do it. Whatever. The point is, it's like trying to save lives is the whole goal of this thing. Okay. I would be remiss if I didn't mention the applications in connection with the smart grid and energy. One of the biggest problems, and Professor Yella talked about it, right? We are at a crucial junction in our society where the number of carbon emissions we're outputting every year is causing greenhouse gases and climate to change and rise in some places and lower some places, and we've seen the hottest years on record. All those things are very scary. So one of the things we need to do is, can we use all of our skills, all of our collective skills with computing to help with the energy problem? We may end up running out of energy at some point where we have a larger demand than we can actually produce. We haven't hit that point yet. But also, we need to be more efficient about things, okay? So the computing can help in many, many, many ways. You can just think about 5 or 6 of them. Number one, it can remind you, computing can remind you and know when if you had smart motes with these little teeny motes here, You can have smart moats that are in the room and can sense movement. And very easily, they can then turn the lights off if there's nobody in the room. Like, you know the idea that you have rooms that turn off if there's no motion? Imagine that in every room all over the world. That would save tons of energy of just wasted lights that are on for no reason, okay? So that's number one. 2, the old model of having one big set of producers that produce the energy, and then they're used by the consumers, all of us. How about people who drive a car and then have their car filled with batteries, a battery-operated car like a Nissan Leaf or any battery-operated car. It parks it. Your neighbor needs some power. So rather than all the power always coming from kind of PG&E or the front-loaded producers, why couldn't they just borrow a little bit of power from your car if they needed it just to handle some stuff? You could basically handle, you guys probably don't remember this, but we had blackouts in California some years ago. Remember that at all? Blackouts? They had this thing called rolling blackouts. We didn't have enough power to handle it. This model could work. It's because all the producers didn't have the power for all the consumers, people who lived in like Walnut Creek, people who live with high air conditioners. So you can imagine a world where, well, my car has some power. You can borrow it to power your dryer or your heater or your air conditioner from 7 to 9 and then give it back to me later. So it kind of even out the power like a battery often does in an uninterruptible power supply. All right. So that's the optimal peer-to-peer routing. Also, moats could be used for incredible other things. Moats could be used and like implanted be so small, these little teeny little computers, implanted so small they form a dynamic grid. You can implant them in paint. The pitch I've heard is they put them in paint. You paint them on the wall, and all of a sudden these moats would wake up, get power from the ambient light of the room. That'd be cool. Automatically talk to the internet. One of them designates themselves, I'm the internet connector. I'm like the head moat, and I'm going to learn from all of you guys in paint, but I'm the one who's going to be a little bit heavier, beefier, in the corner near a power supply maybe, and I'm going to talk to the Wi-Fi system. And that means that room can then have a full sensor network for free because it's in the paint. All you have is this one little plugged-in version. What would that mean? You could, again, know about motion in the room, which could be used for not only turn the lights off, but also for motion detecting for theft issues. You could have fire, so that sensor could smell any smoke. And immediately, not just have one big sensor that knows when a fire gets to that thing up top, but it could all smell smoke and heat around it. So anything abnormal, all those moats could wake up and do something. Also, moats are really useful in military. You scatter these things out, and then there can no motion, so if the enemy's coming towards you, the moats can wake up and say, there's somebody crossing, or maybe it's just a deer or something like that. Okay? So, good stuff. So, in summary, this is not about the applications of computing, but how to compute and where computing can go. This is an amazing time we live in, but a scary time with all the climate issues that are there as well. So one of the things I suggest you do is really find a problem that you would love to work on and help contribute to moving one of these things forward, moving existing technology forward, the existing model of how computers work. You could go in the quantum space, you can go in the biology space, you can go in the energy space. There's a lot of open problems. So I want to leave this as a challenge to all of you to think of the open problems and where you might fit in solving the world's open problems. So we probably can't even imagine the breakthroughs that are going to happen in the next 5, 10, 20 years. Nobody saw the iPad. No one saw the idea that people are going to want to have a little device that you touch. No one saw the iPhone and smartphones. Really, nobody really did. Maybe one person, but no one really, maybe Steve Jobs did, but no one really saw that. What's the next thing that's going to fundamentally change everything for you guys? Be part of that movement. Go, guys. I'll see you on next week.